many might call a recreational math problem, but I can prove it to you using modular arithmetic. Now the statement here is given any integer between 1 and 999. Multiply it by 143. Take the number represented by the last three digits of this product and multiply it by 7. The number represented by the last three digits of this result is the original number. Okay, so if you want to, we'll just, in other words, if you take any integer x, they're claiming after you go through all of this, you'll get back to x. All right, and this is explain why. This came out of Tattersall's book, a guy who was a visiting professor at West Point. But this is an example right below here. So I took a number 200, that's certainly between 1 and 999. Multiplied it by 143, that's an easy mental multiplication. Now notice this remainder here is 600, okay? Or the last three digits, excuse me. All right, now you multiply that again by 7, you get 4,200, and notice you end up with 200 right here, 200 right here. That's what it's saying, okay? And so this is a concrete example of what all the blue text states, okay? It says explain why, and I'm going to do it more in terms of just modular arithmetic. Now there's a fact here that's very important as far as the way I'm going to prove it. Any integer is congruent to its last three digits modulo 1,000, okay? In a concrete example, let's say we have 4,562, let's say, okay? Now, this is congruent, double the triple bar equal sign. This is congruent to 1,562. And they're both congruent to 562, which is the statement, okay? That's important here, okay? And I'll put, for brevity, I'll just call this mod. Modulo is an abbreviation for a modulo, but that's mod 1,000, okay? Now what this really means, folks, is if you divide 1,000 into 4,562, you get a remainder of 562, which is the last three digits. The same with 1562 and the same with 562. So this is a nice little result because it's going to make this proof very, very quick. Now, I like x is an integer in this set from 1 to 999, all right? Some people like to write that x between 1 and 999, but this is very explicit. Between is a little ambiguous sometimes. But so here's what it says, and this is a direct translation. I took 143, multiplied it by x. See, that's what it says right here. Okay, 143 times x. Now it's going to leave a remainder, and probably that remainder, this should also contain 0 a priori. Now it may not be allowable with 143, but in general, your remainders, if you divide something by 1,000, would be from 1 to 999. Okay, so this is just a translation of the first statement. Okay, now what do you think we're going to do next? We'll multiply by 7 here. Okay, we're going to multiply by 7 because that's simply what the problem statement says to do. So this congruence by 7. Okay, we're multiplying, and again, you can multiply through a congruence just like you can multiply through an equality. Now, 7 times 43, if you do 7 times 43, 143, that is 1,001. And that's the miracle number here for us, because this only leaves a remainder of 1, so it's effectively equal to 1 mod 1,000, okay? So this is I multiplied this congruence by 7, so you get 7r, and we were supposed to multiply, see the last by 7, multiply the last three digits by 7, which is exactly what this is right here, right? Okay. So now, but here's the catch, and this is what makes the problem, fairly simple in terms of just proving, a rigorous proof. 1,001 divided by 1,000 leaves a remainder of 1, and sometimes modular arithmetic is called remainder arithmetic for that very reason. So this may be superfluous, but I will write this as 1x, okay? And that 1 is the remainder that you get when you divide 1,001 by 1,000, okay? But you see it's QED time. Okay, that means these both have the same three-digit remainders. Okay, remember what I showed you right here. Everything is congruent to its three-digit remainder if you divide by 1,000. And so that means 7R has the same last three digits as X. 7 times R has the same last three digits as X, which is exactly what we're supposed to do. It says, the number represented by the last three digits of this result is the original number. Well, remember, X is our original number, and that's what this congruent statement actually says. Any two objects that are congruent to each other, mod 1,000, have the last same three digits, okay? If it was mod 100, it would be the last same two digits, okay? So anyway, it's QED time. We approved it. And I'll put a little bit more about it. I think this was problem 19 in Tattersall's number theory book. And he had a very nice section called the, what was it? The intriguing natural numbers. And he had a lot of stuff which a lot of people these days would call recreational math. To me, this is right on the margin of being, it's a very wordy statement, but it admits a very formal, sort of curt mathematical description. Okay? All right. That is all. Thanks for viewing.